Hello everyone, I'm Ishtaweera. So today I'm going to talk about how to describe our robot in the robot operating system. So to start off with, first let's refresh our understanding about what is a robot. So as in the beginning of this session, Dr. Ranga actually refreshed the idea of a robot. So robot is actually a machine that is capable of sensing its environment, carrying out the computations to make decisions and perform actions in the real world. So similar to humans, robot also can sense the environment. So as humans, we sense the environment using our 5 senses, like seeing from our eyes, and then from our ears, we get the sound. Likewise, robot can also get this data from the environment and then do some planning and computation from the robot brain. So we also have a brain as humans, so the robots. And then to perform some actions in the real world, robot has actuators. So similar to us, we have our hands, and we can even use sound output like this, like I'm now talking to you. So similar robots can also do it. So in a robot, there's this basic framework that mostly apply. So this is called the sense, plan, and act framework. So this sense, plan, and act framework is like a cyclic framework. There's no such a beginning or the end because it always perceives the environment, that means sense, and then plans on to obtain a specific goal or some objectives, and then actuate in order to achieve that task. So for an example, let's take our most famous type of robots that we make during our undergraduate life, which is a line following robot. So in a line following robot, we take the IR measurements using sensing, and then using planning, we have our PID control algorithm to control the robot to follow the line. And then these output data is actuated using our motors. So we control the speed of our motors in order to turn and follow the line. So there are lots of sensors that is out there in the market. So these sensors can be sound sensors or perception sensors like cameras, and then mapping sensors like LiDAR. So there are lots of types of sensors out there. So from these sensors, this data is captured, so as an input to the system. And then we have the planning phase. So in this planning phase, there can be many different types of algorithms. So for a line following robot, we use the line following algorithm. And for a wall following robot, so we want to keep some certain distance from the wall by following the wall. And then in mapping and navigation, so we have different sets of algorithms like SLAM and more. And then after we plan, and then we get the output to actuate. So then we have to actuate. That means we want to do some changes in the real world. So for them, we use actuators like motors and even sound actuators. So there are different types of motors that is out there. Maybe you have already worked with few motors like stepper motor and the micrometal gear motor. So likewise, this is the framework that defines a basic robot. So let's see how these sensors and actuators and this planning happens in an example robot. So this is the robot that's at the moment in Mars. So this is the Mars Perseverance rover. I think you may even heard about it or searched about it. And so in this robot, there are actually 2 robots inside. So even there's this Mars helicopter inside, but we will first take this robot and then analyze its sensors and actuators. So for sensors, we actually have lots of sensors, but in this picture, so we have highlighted several sensors like the subsurface radar to capture the radar image, and then the laser micro imager, and then it also have a zoomable panoramic camera, and then this ultraviolet spectrometer, and even an X-ray spectrometer. And to get the weather data, there is separate weather station. So likewise, there are lots of sensors to take input. And then to to plan, so there has to be some sort of a computer inside the Mars rover. So in the Mars rover, they actually have several microprocessors and processors inside Mars rover as well. So they use Intel Atom processors. So in our computer, we have like Intel Core i7, but in the Mars rover, they use several of Intel Atom processors. And then for actuators, there are several actuators you can see even in the Mars rover. So here you can see a robot arm. So that is used to actually change the orientation and the displacement of this ultraviolet spectrometer. And then here we have several motors to control the 6 wheels of the robot. So likewise, so now you know that many robots actually come with this system of sensors, then planning, that means computation and actuating. So when we have a robot, we have to introduce it into robot operating system. So how can we do this? So for this, we have to first understand the foundation that is used to describe a robot in ROS. So the first thing that we have to know is the coordinate transformations. I think you all know about the Cartesian coordinates, the X, Y, and the Z. So normally the X direction is denoted in red color, and then in blue is the Y direction, and then Z is in the green color. So in this image, the green arrow is pointing upward from this plane that you can see, the screen actually. So in ROS, we define these coordinates in a tree-like structure. So that means each frame has a parent, and a parent frame can have different children. But as humans, a single frame can only have one parent. So that's why it's like a tree structure. So here you can see a small example that a robot is displayed in the space. So here you can see actually 5 frames: the map frame, the odometer frame, the base footprint, the base link, and the laser link frame. So here you can see the TF tree. So as you can see, this is like a linear tree. I mean, there also can be branches as well. And when we define a frame in coordinate transformations, we define it as a relative transformation to its parent. For that, we have to define the relative transformation in the in like both translation and rotation. So for that, so we can define the XYZ translation and then the yaw, pitch, roll, rotation with respect to the parent frame. So in ROS, we have a separate package called the TF2 package. So earlier there was this TF package, but now with the additions, we have TF2 package to handle these coordinate transformations. And using TF2 package, we can do many tasks like compute the forward kinematics and even the inverse kinematics. So for an example, you can run a command called ROS run TF2, TF echo, and then the parent and the target, I mean the source and the target frame, and then get the computation, I mean the relative translation and rotation from the source to target frame. So here you can see the most famous PR2 robot. So this robot is similar to a human. So it also has a head, a neck, and chest, like 2 arms, but it doesn't have legs. So here you can see that so inside a robot, there are lots of coordinate transformations. So in arm, there can be some coordinates that actually move. So those are called dynamic frames. And then there can be some frames that are actually static. That means they are fixed to each other, so they can't move relatively. So in coordinate transformations, likewise, there are 2 types of frames: static frames and the dynamic frames. So static frames are mainly used to define fixed joints. So in ROS, we have a package called Static Transform Publisher, package to manually transform static transformations. For an example, we can run a command called ROS run Static Transform Publisher XYZ yaw pitch roll. That means the relative transformation from the parent frame to child frame. and then we have to denote the frequency, and then we have to put in the time. So that means 1 over frequency in milliseconds. So then the other type of frames is the dynamic frames. That means those frames can move with respect to its parents. So mostly these types of frames are used to define the movable joints, which are translational and both rotational. Right. So now you have an understanding about coordinate transformations and how different coordinates can be defined in a tree-like structure. So by using this in ROS, we have to define our robot, and there's a certain policy or some type of format to define or to introduce our robot to ROS, and that is called the URDF, Universal Robot Description Format. And in URDF, we have to define these frames in terms of links and joints. To understand that, so let's take our human body. So in our human body, we have our head, the neck, and the arms. And there are certain parts that don't move with respect to each other. And there are parts that can move with respect to each other. Like for an example, take the arm. So we have a joint here, which is where we can rotate this limb with respect to this limb, likewise. So for a robot also, we have different types of joints. For an example, let's look at a few common joint types. So one type of joint is a revolute joint. So in revolute joint, one limb can rotate with respect to the other limb. But there's a range of motion, like the minimum and the maximum range that it can rotate. For an example, in an arm, so in an arm, we have certain degree that we can rotate. So we can't even we can't turn this 360. So if that happens, that means our arm is broken. So that is the revolute joint. And then we have the prismatic joint. So in the prismatic joint, two links can move each other in a translational manner, not the rotation. And then we have the continuous joint. So this you can see in wheels and encoders. That means it can rotate, but there's no range of motion. The range can be infinite. You can turn as many times as much as you want. And then we have the fixed type of joint. That means the two objects or the two links. So links are the things that actually connect together using a joint. So these two links are fixed together. That means they can't move. So then one might ask, so why do we need to have fixed joints? So can't we take these two links and make it a single link? Why do you think that we have to define two links and they connect it using fixed joint? So most of the time in robots, we have some parts that can be removed or customized. Like for an example, for a robot, there can be a camera adapter. But sometimes we don't need the camera adapter and then we can remove it. But when it's attached, it stays still. I mean, without rotating or turning. So then these types of connection, we can use a fixed joint. Now you know like some common joint types. So back into URDF. So in URDF, what we do is we define these links and joints. That means different sensors, actuators, and how they place in the 3D space, and then connect them and then define them in a way that ROS can understand. And the language that is used to define this is the XML format. So similar, like bit similar to HTML. And so inside the URDF file, so we first have to define the XML version. And here you can see a basic structure of the URDF. So you have to start with the robot tag and with the robot name. And now there's a new tool called Zacro. So that means we can divide the URDF file into several types, several files, and then connect them together. So in that case, we have another section to define the Zacro. Right. Yeah, so moving on to the next slide. So now let's look at a small example of how to define this in URDA. So here you can see a small application of a robotic system. So this is a camera slider platform. And then you can see here there are 4 links and then 3 joints. So always the number of joints is less than number of links. So these 4 links are connected using 3 joints. So here we have the base and the slider and then the arm and the camera. So between the base and the slider, there is a joint. And then the type of joint should be what? Prismatic joint, because it has, so these 2 links has to relatively move. And then between the slider and the arm, there's this revolute joint because it has to turn, rotate. And then between the arm and the camera, so here in our example, we use a fixed joint, but it doesn't have to be fixed. Like for an example, if we want to tilt and pan the camera, we can even attach another, like something on top. So inside URDF, inside the robot tag, we have to define each link and each joint. So here you can see how we can define a link. So in a link, we have to define a link, we have a link tag. So inside, we can give it a name using, like for an example, here we take the arm. So we name it as the arm link. So inside the link, we have 3 different parts to define: the visual, collision, and the inertial. So in the visual data is the data that we put such that the ROS, like simulations or the robot model tools that can understand its visual appearance. For an example, its size, the geometry, where it should be placed, and then the material, like the color or other descriptions. And then we define the collision. So for an example, think that there's this path planner, and it has to plan the path in a way that it doesn't obstruct with something else. So for that, in order to calculate those things, we use this collision tag. So for most of the complex systems, sometimes these visual details can be complex, but the collision geometry will be defined in a easier way in order for easy calculation. And then we define the inertial parameters like the mass, origin, and the inertia. So the inertia means we need to define the IXX, IYY, IZZ, and then the other 3, like all of together 6. So that is how we define a link. And for this system, we have 4 links. So we have to define, like for the base, slider, arm, and the camera. And then how to define a joint. So here is a small example of this arm joint. So in the to define a joint, we have a separate tag called joint and then the name of the joint. So here we have the arm joint and then the type. So here we have the revolute joint. And then we had to define, so what is the parent frame and the child. So what 2 links are actually coming together with this joint, and then the origin of it, and then the axis of rotation. So here the axis of rotation is the -y. And then the limits. So the lower limit and the upper limit. So these are in radians. So that means like the upper limit is 90 degrees, and then the velocity in radians per second, and the effort, that means the maximum effort in Newton meters. So after we define this URDF, so this can be visualized in tools like ROS or Gazebo or any other tool. And then this, so you would see a similar type of, visual that like this. Right. So the next question for you, I think, might be, so this is some kind of a complex procedure. So we have to define all of this, and then the geometry, like for an example, think that in a complex robot like this, how can we use like simple shape like sphere, box, or like a cube to get these complex, objects. But if you design your robot in SolidWorks, so this is also for SolidWorks, but for the tools as well, there may be some add-ons. So in SolidWorks, there's a tool, an add-on called SolidWorks URDF. So using that, you can easily convert into a URDF format. And then so you might have to maybe rename or configure a bit. So like the link names and the join names and maybe the colors of the materials, you can even customize later. Right. So when you have the URDF file, so let's look at how this URDF pipeline works. So there's a pipeline in ROS, so how it understands URDF and what to do next. So as I previously mentioned, for complex robots, there may be multiple URDF files, not a single. And there's something called Zacro in ROS, so which actually takes these multiple URDF files and then produce a single URDF file. And then that URDF file can be read using a package in ROS called the Robot State Publisher. And then it publishes two tokens. So one is the TF static and one is TF, and then the other one is robot description. So this TF static includes the fixed joints and its transformations. And then this TF includes non-fixed joint transformations. And then the other description like the material and how can it be visualized, how to calculate the collisions is included in the robot description. So using this information, you can, subscribing to these topics, ROS can give you similar visualization like this, right? And then, so when we have dynamic joints, that mean like dynamic frames, that mean joints that can rotate or translate with respect to the links, you have to control this. And for that, this Robot State Publisher package subscribes to a topic called joint states. And by publishing joint state to this topic, you can easily control this robot in ROS. So there are normally 3 ways of doing this. So in the designing stage of URDF and the robot system, so we manually publish these joint states. So we can use another package called Joint State Publisher GUI, and using that, we can publish joint state. And in the simulation stage, we can use like simulation platforms like Gazebo or Unity or some other tool in order to publish the joint state into this topic. And in our actual robot, so we can use this real actuator feedback to even publish to joint states. Right. So now you have an understanding of how to describe our robot to ROS using URDF and its pipeline. And let's briefly look at some robotics applications in ROS. And then the first one is the robots that doesn't walk or travel from one place to another. So those are called robot manipulators, but they have robot arms. That means they have like arm like a human that can do tasks. So these robot arms are actually very famous in the industry and has been there for a very long time. And it actually consists of a kinematic chain. That means a connection of links and joints that can rotate or translate. So here you can see a robotic application in the Tesla manufacturing facility. So you can see there are many, there are like hundreds of robots that do painting jobs, mounting and inspection and lots of things. Let's take a small industrial, an example of industrial arm, KUKA KR210. So in this robot arm, there are 6 joints mainly. So one is here, and then the second one here, and then the third, the fourth, and fifth one, and then the last one in the end effector. So here you can see like the mechanical diagram, and one concept that you have to know is about the robot workspace. That means that in a robot arm, it cannot reach all of this the location in a 3D space. So it has some certain of XYZ locations and the end effect orientation that it can reach. So that is called the workspace. So in ROS, there are tools like Move It where you can calculate the workspace. Right. So let's see. So once the URDA file is defined, as previously mentioned, so you can visualize this robot in ROS. So here in ROS, we use the first type of way to control the joints. So as I mentioned, there are 3 types, and this is the first type using the joint state publisher GUI. So using that, we can change the states of 6 joints, and based on that, the robot state publisher package actually visualizes, changes the TF and subscribe to TF is the ROS, and then it visualizes. Right. So then we have the inverse kinematic. So this problem is different to forward kinematics. Forward kinematics is actually defining the joint states directly, and then from that there may be some particular place where the end effector is. But at sometimes in most of the applications, we have to control the end effector, not the position of the each link. So we need to, control the end effector in a way that to achieve our application. So those are called inverse kinematics. So in that, we have to calculate the joint states in order to reach the end effector in the certain translation and the orientation. So in ROS, we can do it. So there are tools like Move It, or we can use the TF2 library to do it as well. So here you can see like a small visualization of how inverse kinematics works. So what this is trying to do is it tries to follow the ball, that the green ball here. And you can see that at some points, it fails to follow the green ball. So why do you think that it would happen like this? So the reason for that is, as I mentioned previously, there's this workspace. So there are like certain locations where the end effector can't reach. So in that occasion, the arm cannot follow the green ball. So let's look at another application, which is the robots which can move from one location to other. So that is called robot locomotion. That means act of moving from one place to another. And there are lots of robot locomotion types, and let's look at a few of them. So the first one is legged locomotion. So here you can see a quadruped robot which has 4 legs, and then we have a bipedal robot that walks like humans, but this is a bit ineffective way for robots. And then we have wheel locomotion, and then the track locomotion like the tanks, and then the propellers. So for mainly aerial vehicles. So here you can see a small example of differential drive system. So on the left side, you can see the gazebo simulation, and on the right side, you can see the ROS visualization. So here you can see like the second type of control. That means using the gazebo, it actually publishes the joint states, and then we can control the speed and the rotation, speed and the direction of the motors. And this is the simulation of a Mars rover in both ROS and gazebo. So you can try these examples leisurely in construction. And then here you can see 2 examples of the robots that we built during our first year, maybe undergraduate life. So we developed line follow and word follow robots. So you can do this as simulation. So in actual robot in ROS. So to recap what we learned, so robots act in a sense, plan, and act framework. And in ROS, to introduce robots, we use coordinate transformations, and TF2 library is what helps for that. And to introduce our robot to ROS, we use ROS URDA format to describe the robot, which in a way that understands for ROS. And then we talked about 2 examples of robotic application. Yes, so that's over. So thank you, and over to you.